Alright, so in this video we're going to go over the problem called the Maximum Rectangular Subarray Problem. Sounds very fancy. It is a fancy problem. It's not on the easy side, but once you get the hang of it, you'll be able to solve it relatively quickly. And not only that, but there are many problems that you'll be able to solve faster and easier once you understand how to solve this problem. Alright, so we'll first go over the problem, what it's about, and then I'll show my steps on how I approach the problem, as which you could regard to also approach the problem itself. And after we consider the solution and the mechanism behind the solution, I'll finally show the code that passes this problem, and we'll go on line by line and function by function to see how the code works. All right. So what's the problem about? Well, essentially, you're given a series of points, right? You see a hell lot of points here. Each of the points have specific values. So you have 2, -1, 3, -1, -1, -2, and 5. And as you can see, they're put on a 2D coordinate plane, meaning that each of them have points x and y that are unique to themselves. So this could be x1, y1, this could be x2, y2. You get the hang of it. Each of these points have specific coordinates attached to them. Your job here is to find the maximum rectangular sum. Well, what do I mean by that? Essentially, you could draw a rectangle anywhere on the 2D plane. Sorry, that's a bit. Show a cleaner one. So let's draw a rectangle like this. Well, the sum of this rectangle is defined by the sum of values of all the points that are within the rectangle. So within this rectangle, you have the points 2, -1, and 3. So the sum of this rectangle would be 2 plus -1 plus 3, which is 4. So as you draw different rectangles, for example, if you draw like this, you'll also have a sum of 4, right? But notice that if I draw a rectangle like this, right here, now you'll have the sum of 5 plus 3 plus -1 plus -1, which is 6, right? And you can see how the sum of this rectangle is bigger than the sum that we previously found from the orange rectangle. So as you can see, the sums of rectangles would vary based on the location and the size of the rectangle that you create. Your job is to find the maximum potential sum that you can make using a rectangle. So in this scenario, the answer to this problem would be the rectangle R. You can see that within the rectangle, you have the values of 3, -1, and 5. So that yields the value of 7. Right? And this is bigger than the previously found two values, 4 and 6, right? You don't have to mention the dimensions of R, you just have to tell what sum R would contain. And also, there isn't a guarantee that there is only one answer within the coordinate plane. There could be multiple rectangles, actually, that all yield the same sum as this R right here. It's just the problem's asking for the maximum potential sum. It's not asking for how many of them you can make, right? So all you have to write out in standard output is the sum that you could create using this rectangle R, the maximum possible sum. The constraints for this problem are pretty important. This problem comes from the Korean Olympiad in Informatics, also known as KOI. So the problem is written in Korean, but the only things that you have to really be careful of are the constraints here. Let's go over them individually. So n is the number of points. And this is a positive integer that is less than or equal to 3,000. X comma y are the coordinates on the 2D plane, and both of them are less than or equal to 109. And greater than or equal to 0. Finally, you're given W. This is the weight, basically the value that each of the points contain, right? So this W is less than or equal to 109 and greater than or equal to negative 109. So these three are the constraints that are given, but in my opinion, the only constraint that you have to keep in mind of is the first one, the constraint of n. I'll go deeper into why this is specifically important in a moment. Anyways, that's the problem. Now we'll go over to actually solving the problem and thinking of how we could tie this with a segment tree. Alright, so how do we solve this problem? Well, before that, let's take a step back and think about how we used to solve things when we had to find the maximum subarray of just one-dimensional scenario, right? So what I'm saying here is, if you're given an array like this, just a traditional one-dimensional array named A, for instance, where we have values here, how would you find the maximum potential range sum of this array? Well, there are many ways to do it, but the most efficient way, which takes O of n in this case, would be to put the pointer here first and then traverse through the array where if the net sum from, so let's say we start here, right? We would start adding in the sum place, we would add x1, x2, and so on, but only if the net sum is equal to a positive value. So what do you mean by that? If x1 was negative, there's no reason to really add it into our maximum sum calculator, right? Because we could just simply put the starting point here, or anywhere else that doesn't include x1, right? The same logic applies if we traverse through the array, right? If we kept adding x1 and x2 and continued to update the maximum sum, so we updated x1 here and then x1 plus x2 here, and then we continue to do that. But then if x1 plus x2 plus x3 is less than 0, then there's really no reason, right? If we're gonna include here, there's really no reason to include this subarray, right? Because if we want to include some other value past this point, then that means we have to include this subarray, right? Sorry, this subarray. And we have absolutely no reason to do that. So in that case, we would ditch the array and then reset sum to 0, and then just have a fresh start here and then do the same process, right? So anyone who has not heard of that algorithm, I believe it's called Kadan's algorithm. You could search it up and learn this on your own. But anyways, that is the most well-known way of how you would solve this scenario for a 1D array. Now the question is how you're going to move this logic, or just the problem itself, into a 2D scenario. And you can see here that unlike how I displayed it here, this image is tilted 90 degrees to the side. And the reason you'll understand later on, but let's think about another scenario for a second. What if you're given the same array A of size n, from x1 all the way to xn, and it's the same scenario. You got to find the maximum range sum, but now the scenario changes into these values arbitrarily changing. So for example, if x1 was 3, then there might be a query to change x1 from 3 into -1. Well, in that case, this Kadan algorithm wouldn't work out, right? Because you have to traverse from here, the starting point, all the way to the end point. So it'll take O of n. But if there are n queries, then that'd be O of n squared, and that would mean inefficiency. So we need a better way to do it, right? So in this scenario, segment trees can come in pretty handy. And I'm going to introduce you a specific form of segment tree that you could use to tackle such problems of maximum subarray. So we'll need a new page here. So let's have a struct C like that. I'm writing like this so that later we'll represent it as C seg tree segment tree of type this struct, right? Just like how we write int seg tree. We're going to define this struct, we're going to define this object as C. So what's going to be included in this struct, right? Well, there are going to be mainly 4 things, I believe, if I counted it right. There's first going to be tot sum, total sum. And then we'll have left max. I'll introduce each of them in just a moment. Anyways, we have tot sum, left max, right max. And then we'll have tot max. Yep, there are 4 values. Well, what do each of them mean? Well, tot sum is literally the total sum. Array being handled. So basically this means if we have an array of size n and we try to use a segment tree related to this, this segment tree node would be handling all the values from 0 to n. When it splits, this left child will only handle from 0 to n divided by 2. And this right child will handle from n divided by 2, or the midpoint, plus 1 all the way to n minus 1, right? Basically, it's just saying, whenever you split this, the left child's going to get this portion, and the right child is going to get the other portion, right? So the right child gets this portion. Okay, so that is tot sum. Well, what do the rest of the 3 mean? So tot max has a pretty straightforward name in my opinion. Tot max is the maximum subarray sum, I guess, maximum range sum. So basically it's just the problem statement, right? When you're given this array, you're trying to find the maximum possible range sum, right? What range gives you the maximum possible sum? That's what you're finding, and tot max is exactly defined by that. So in other words, if you want to talk about the entire array called A of size n, the answer would be put on segment tree mother node dot tot max, right? Because the mother node, it handles the entire array, and tot max should be putting the maximum range sum value, right? So that is tot max. Now the other 2, left max and right max, it might be counterintuitive at first, like, I mean, why you would include it, but once you understand it, it's gonna look elegant, right? So left max, this might be better off introducing with a picture. So let's say that a segment tree, a specific node, is handling this portion of an array, right? So left max is trying to find if you have to start here, right? If your left end has to start here, then what's the maximum possible sum you can make? Maximum possible range sum, right? So remember how the maximum range sum problem, you could set the range any way you want, right? Like this or that, or even like this. But in this case, for left sum, your left end is not free. It's stuck into the very left side of the array. Now your job is to find what right end would yield the biggest value. Now, similar thing goes to right max, right? Right max, oops. When you're given an array, in this case, your right end is stuck right here. So now it's asking if your range sum has to start here, then what left end or what range yields the greatest range sum? So right max and left max, they're basically the same by definition. It's just that which side they're sticking onto or keeping it fixed is the opposite, right? For right max, you're keeping the right side fixed. For left max, you're keeping the left side fixed. Well, why is that important? Well, let's think back to how segment trees work. Remember how in order to have the value here, or the mother node, segment tree's first value, you got to merge the child nodes, right? So if you have left child and right child, seg tree's mother node is by definition equal to merging the left child and the right child, right? So far this is pretty straightforward knowledge. Now the question is why this relates to having left max and right max values. Well, think back to what other values we had in the struct. We have tot sum, but we also have tot max. Tot max is the one that's actually important that we need to find from here, right? Tot max. Okay, then let's zoom into these children nodes, right? So this means that each of these children will have a tot max value. Now the problem is these tot max values aren't complete. What I mean by this is this tot max is only thinking about this range of array. It's not thinking about any values from the right child. Likewise, the tot max for this side is only using the range within this blue part. It's not thinking of any of the values or ranges that include the red part, right? So whenever we think about the mother node, we have to find the mother node tot max. Well, we're also going to put compare these two tot max values, but we'll also need a third value, another tot max, where it'll incorporate both of these children nodes. And here's where right max and left max comes in. By definition, tot max is equal to the maximum possible sum, range sum that you can make, right? And if we're going to include both the left child and the right child, right? If our range has to include both parts from the left and right side of the array, well, that inevitably means that we're going to merge these two ends together. They're going to be merged up close. Okay, then if we merge it like this, oops. Well, what does that mean? Well, our maximum tot sum, incorporating both of the arrays, will look something like this. If we use another color, looks something like this. If this looks somewhat familiar, you'd be correct, because here, this part is equal to the left max. That is saved within the right child. Likewise, this part is equal to the right max, saved within the left child. We know that adding the two of these left max and right max values will always yield the maximum possible sum when we have to incorporate both of the childs, because by definition, choosing the left max value, it doesn't have any relation to do with choosing the other side's maximum value. And since we have to merge these two together on the midpoint, our endpoints have to start within here. So if we only include the two possible maximum values we could achieve by going this way and by going this way, then automatically adding those two would give a third potential total max value, the maximum range sum value. So that is how we merge the two nodes, children nodes, into finding the total maximum value. Okay, so if we got that out of the way, why would we also include a total sum value, right? Because remember, our struct also had a tot sum specifically. Well, this also has something related to the fact that the left max and the right max here, the left max has to start at this endpoint, right? But the only left max that we have right now is the left max that only considers the red portion of the array. It never tried to spread until the blue side of the array. Likewise, for the right max value here, you can see that it only considers spreading up within the blue array. It never spread until here, to the point of which we'll try to find the range sum of here and compare it, and potentially it could be the new right max value. So in simple words, whenever we merge the two children nodes, we'll have to update left max and right max of the mother node so that we could try also incorporating this portion of the right child node for the left max value, try spreading all the way here beyond the red array, and likewise for right max, go beyond the left endpoint of the right child and then try to find a new range that could yield a bigger right max value. Okay, well in that case, by definition, if we have to incorporate the other side, it means that we have to pass this midpoint. Well, within the midpoint, if we're looking at from this standpoint, this means that we're going to include all of the red left arrays sum. Now that is tot sum. Likewise, if we're going to find a new value, potential value for right max, that incorporates the left child, it has to cross the midpoint. So it'll inevitably include all values of the right child. And that is equal to the tot sum that's stored within the right child node. So that's how you update the left max and right max for the mother node, and that is how you use all the four values within the struct. Okay. So we found that. Now what do we know? We know how to find the maximum range sum or maximum subarray of a one-dimensional array, with the catch that specific values could be updated. Now, is there any way we could incorporate this concept into solving our original 2D maximum subarray problem? Well, yes, there is, and now I'm going to introduce how to do it. Let's first erase this. Now, before we try to update things, right, let's first just try to find the range sum of the biggest rectangle that we could draw, which is incorporating all of this. Well, if we are going to draw the biggest rectangle, that includes all the points we don't really need the nuance of continuing to save the specific x locations, right? The x values of the coordinates. All we need to do is just have another 1D array, maybe here, and just drop these points down to be plotted onto this 1D array. So if we do that, it'll look something like we'll have 5 firsts, and then -1, -1, 3. We'll have -3 here because these are on the same coordinates, and then 2. This looks familiar, right? This is also a 1D array where you could find a range sum with a segment tree. Okay, well, let's twist the problem a little bit. Imagine that our endpoints are fixed here and here, but we could modify where we cut the rectangle vertically. So basically means with our new restrictions, we could draw a rectangle like this. But you could also draw a rectangle like this. So even if our endpoints here, the upper endpoint and lower endpoint are fixed, our left and right endpoints are not fixed. Well, in that case, what's the maximum possible sum you can make with the rectangle? Well, okay, well, we plotted the points onto this 1D array. Now the question just becomes how we set the start and end to make the maximum possible range sum. And now that is the same problem that we just solved regarding the maximum subarray of a one-dimensional array using a segment tree. So we found out that under the constraint that the upper and lower points, the endpoints are fixed, we could find the maximum possible rectangular sum using a segment tree with a struct with 4 values within each node. But that's not the question, right? The full question is we could also modify the upper points and the lower points, right? Well, in that case, how are we going to be able to solve the problem? Now, at the surface of it, this might seem too complicated to solve. In fact, it might seem like our approach lies short here, but it's actually not. We could extend the problem using the same algorithm and idea that we just used. Now, why, you might ask? Because it seems like there are too many points. But if you think about it, we have 3,000 of these points at maximum. Now, 3,000 might seem like a large number, but if you think about it like this, 3,000 squared, which is equivalent to thinking about O of n squared time complexity, that only yields 9 million. Now, in competitive programming, that is definitely not the largest possible number, right? You need to go up to like 10 million or 100 million even to think of it like a big number. 9 million is small enough. Especially when it comes to segment tree queries, 9 million is not a big number. It's doable. Okay, well, we found out that n squared is doable. Now, how are we going to use it here? Well, let's, instead of putting the lower endpoint, like here, fixed at first, let's dynamically move our upper points, lower points, sorry, I mean. So we'll start it here. I'll erase the other things. Now, okay, we'll put the lower point here, and the upper point like this. Now, since with this plot we can't really adjust the upper point to make like different sums, we'll move down the lower point just a bit. Let's say like around here. So in that case, we'll have to, with the lower point fixed here, our job is to first modify the location of the upper points. And whenever we modify the location of the upper points, we'll fix the upper and lower bounds and then do the same thing that we tried before to find the optimal range, the left and right endpoints that will lead to the greatest possible range sum. Okay, so basically means at first we'll put the upper point at the very end so that all points are included, and then the array, in that case the array would look like -1, 3, and 2 if we plot all these downward into our segment tree right here, right? Our array, basically. Anyways, so we do that, and our maximum subarray would be 5, right? And after we find that, we're going to move down the upper bound so that it passes 2. So 2 would be out of our equation now. So 2's gone. Now we have to find the maximum possible range sum only using these two numbers. Now in that case, our new range max would be 3. Okay, so we found that out. And after that, we're going to move it once more down. So -1 is also eliminated. And our new range maximum sum would be the same. It's also going to be 3. Now, what we have just done here is we fixed the lower points, but by modifying the upper point and updating so that it erases the points step by step, we made it so that we check different intervals of upper and lower points. And we could also modify the location of the lower end. We just have to do that starting here. The green one also. Okay. We just have to start the blue lower end here and then move it step by step. As we move it, we're gonna do the thing with the upper end. Just put it at the very end and then update it so that it includes different intervals. So if we speed up the process, it would be like, so we put it here, and then we only have 1 point, so we move on. And after that, we set the red point here, find a range maximum sum, put it here, find a range max sum, and then maybe erase it. Yeah. After that, we would do the same thing, but with lower point here, reset the upper point here, find a maximum range, find a maximum range, maximum range, maximum range. Now move that one more lower, and then find a maximum range, maximum range, maximum range, maximum range, maximum range, maximum range. And then you go down one more time. You get the idea. You keep changing the upper and lower intervals, endpoints, and whenever those lower points have been established, you're going to find the maximum range sum within that interval. Now, that's going to take, okay, so because they're endpoints, right? In the worst case scenario, all of these ends will have different coordinate points. So if we move it sequentially like this, in the worst case, we're going to have a time complexity of O of n. But we're going to also, for each time, we're also moving to erase each of the points that we have found before to change the intervals, right? So if our our lower interval is up here, down here, we have to start from here and go all the way down to the very last point that we just found. So that means that we're going to have another n traversals. Technically it's n divided by 2, but it's essentially the same. So that'll lead to a time complexity of O of n squared, right? And each time, for each traversal, we're updating so that the segment tree array doesn't include this value, right? And that's kind of the same thing as saying xi. Remember how here in this problem, our idea is xi could change anytime. We're just doing that here, but just after plotting all the points into a one-dimensional array instead of a two-dimensional array. So xi, we remove that one first, and then our next would be this value, and the next would be this value, so on and so forth. And with updated arrays, we're gonna keep on finding our new maximum range sum. And for segment trees, that update process is logarithmic, so our final time complexity would be O of n squared times log n. That fits well within the time constraints. So that's the general idea of how you would solve this problem. Now we're going to look at the solution code and see how the solution code mirrors this solution idea. All right, so here's the solution code. I'll paste the link to it in the description if anyone wants to check it out. So some namings are different. This object is not actually for the segment tree. This is to store the inputs, right? The x value, y value, and the weight of each point. Our actual segment tree is going to be based on this object. We have the four variables, right? The names are slightly different. We have tot sum, left fix max, right fix max, and max val. Yeah, what they do are essentially the same. The only new variable here is null in Boolean form. This is just to make merging easier. I'm gonna show the merging function in a bit, but this variable is supposed to make things a little bit faster and more intuitive. We have the vector that stores the inputs, and for me, instead of regarding the maximum being 109, I just use coordinate compression, right? I compressed the coordinates that exist and indexed them using binary search. So here is the merging function of the segment tree. As you can see, if the left child is null, this means that the left child doesn't have any array assigned to it. So it basically means the left child doesn't have any use. So in that case, we're going to immediately return the right child. Same goes if the right child is null, we're going to immediately return the left child without having to merge it with a null segment tree node. So after that, our new node is going to look something like this. Our tot sum is going to be obviously the sum of the left child's tot sum and right child nodes tot sum. And our left fix max initially is going to be the lower ones, the left child's left max value, and the right max is going to be the upper right child's right max value. And then for the max val, or the max sum, I think tot max, yeah, for the tot max value, before we do anything, we're going to first find the maximum out of the two that originally exist from lower dot max val and upper dot max val. This is basically the max val that is stored within the left child versus the right child. And is null is obviously going to be false. So after that, we'll have a new value of max val. We're going to compare it to the current one versus the max val that incorporates both left and right child. So that'd be the right max of the left child plus the left max of the right child. It's the same thing that we discussed here when we incorporated. The third tot max is always going to be the sum of the right max of the left child and the left max of the right child. Our left max is going to be compared to itself versus the new one, which is adding the entirety, right? The entirety of the left child, and then adding it to the left max of the right child, right? Same logic goes for the right max. We're going to compare it to itself versus the entirety of the right array, the right child, plus the right max of the left child right here. After that, we're going to return this new segment tree node. Update function, it's just like a typical segment tree function. It's not implementing lazy propagation, so it's pretty straightforward. When start is equal to end, it means we're there. We have the new value, and then we're going to update segment tree, and we're going to update the segment tree value in the return. Yeah, this is what the node looks like when it is down to the most elementary level. So what I mean by this is, if the segment trees node handles only one value, this is what it should look like. We have tot sum, left max, right max, and tot max. These are all the value itself instead of 0 in case the number is negative. Reason being that by definition, left max, right max, and tot max are on the consensus that it uses at least one value within the array, right? So that's that. This part, we're just gonna split the current segment tree range into half and then see where an IDX is located, and then update either the lower half or the upper half. And then after everything's updated, we're gonna merge the left child and the right child to update our new segment tree node. So that's out of the way. After that, here's the main function. We have v that stores all the queries, but we also have chords that are for corner compression. I'm gonna skip explanations regarding the corner compression here, because you could just solve the problem without it, right? So we store all the queries and sort v in terms of sorter, where it sorts it in ascending x value. We traverse through v, and each time we update our new point, right? So w is the weight of the point, and whenever we reach a new point, we're going to update that into our segment tree, right? So after that, this is another if statement. Now, what does this do? Well, one thing that you have to be careful of is, in case there are like multiple points like that on the same line, if we only update this point, then the range sum is not going to be correct, because, for example, if our range is like this, and we didn't update this or this, then our range sum is going to be incorrect. Actually, it has to include all of the points within the same line in order for us to do the operation, changing the upper end and finding the range sum every time, right? So that's the if statement. If we update all the points within the same line, then we update the answer, the maximum rectangular sum. And after that, we have a for loop within the if statement. Now, this is going to be responsible for modifying the upper end. So you see how we updated the weight multiplied by -1. This means that we're erasing the value. After that, the same if statement exists, just so that we check that if all the values within the same line in the upper end has been updated. Once that has been updated, we're going to update answer to see if the current max value is bigger than the answer value that is stored. Once all of that is done, we're going to traverse through one more time so that we updated the values and returned them as they are, the erased values, right? Once that's all done, we're going to return our answer value, and that's the entirety of the code. So that's all for the explanation. I hope you enjoyed watching the video and at least had a slight understanding or some takeaway regarding segment trees and maximum range sum problems. So solving this problem will help you be way more familiar to segment trees, and also divide and conquer problems, I believe, because it uses basically the similar concept, right? Anyways, that's all from me. I'll see you on the next video.